Let me have you add these into your notes. In combinatorics, there is what is called the fundamental counting principle. It's how we're going to count. This is how to count things. If there are A total ways to do one thing, and B total ways to do another, then there are A times B total ways to do both together. I know there's A ways to do something, and B ways to do another, so that means there are the product of A times B ways to do both in total. This is how we're going to count throughout this entire set of combinatorics we're going to get into. Think about how many ways there are to do something. Want to do both? Multiply them together. Let me show you a brief explanation as to why. With a little tree diagram. Go on a short trip. Pack a bag. In that bag, I'm going to throw 3 shirts and 2 pairs of pants. So how many days could I go before I have to wear the same thing twice? 6, right? Sure, because is it 3 times 2, 6? There's 3 different ways to pick a shirt. There's 2 different ways to pick a pair of pants. So to wear both at the same time, would that just mean I have 6 ways in there? Makes sense. Let me see why. 2 pants. Here's the first pair of pants. Here's the second pair of pants. Now with each pair of pants, how many shirts could I throw on top of it? 3. So off of each of these different branches, I'm going to draw 3 more options because there are 3 different shirt combinations there. So all told, how many different options are there? Like you said, there's supposed to be 6, right? 1, 2, 3, 4, 5, 6. Any of the 3 shirts with the 2 pairs of pants means there are 2 times 3 or 6 different clothing options. I can almost make it a full week. Does that make sense? Okay. I like the nice, easy one to start with. I didn't want to diagram out something that has like 30 different combinations. Let's try one more. Go to Spaghetti Works, downtown on Court Avenue. They have what's called the never-ending pasta combination, right? You can mix and match all different types of pastas, sauces, stuff like that together. So how many different combinations are there if I go to order something at a restaurant like that? Let's say I have a restaurant, and they have 5 different entrees to pick from, 6 different side dishes available, and 3 different dessert options. Yeah, you're going to pick one of each. Let's just keep it 1 to 1 to 1. So how many different meal options are there? What do I do with these numbers? How many different entrees are there? So there's 5 different ways to pick an entree. How many side dishes? So there's 6 different ways to pick a side dish. How many different ways am I up to now? 30. But off of each of those entree and side dish options, how many different desserts are there? 3. So there's 3 ways to do the next thing. Am I up to now? 90. 90 different meal combinations. If you take one of each before you have to repeat the same thing. Does that make sense? Let's do this. I got about a handful of questions here on these types of counting problems. Let's take about 5 minutes in class. I'll have you work on these. And we'll talk out loud through your answers. Put this up on the board here for you. I'd like you guys to, like I said, use counting principles and think about how many different ways there are to do all of those options together. Awesome. How many different shoes are there? This question was offered last hour. How many different shoes? Right? The brown pair of shoes and the black pair of shoes, so 2 pairs of shoes altogether. You have to wear the same thing every single day. How many shirts do you have? You have in your own car. Like up to shoes, 1 shirt, pair of shoes. Think about what you have in your car. Shirts. Yeah, no shirts do you own? Do what you want to do.
Bethany Button, please report to the secondary office. Bethany Button, report to the secondary office.
So this is for you. How many shirts do you own? And you're going to pick any one of them. So there's 25 different options in your shirt. Pants. Shoes. So how many days or years could you go if you have to wear one of each of those, or you have to repeat the same amount? 1,100 days? What is that almost? It's not 12 times 2, it's 12 times something else. It's 12 times something, it's not 12 times 2. I'm only picking 2 positions, a captain and a co-captain. 11. All right, let's talk about number 2 for a minute. Let me pause here really quick. Number 2, how many ways can you choose a captain and co-captain from a group of 12 players? Now think very carefully. How many ways are there to choose a captain? How many players could be captain? 12 of them. How many ways are there to pick a co-captain? How many different players could be co-captain? Why 11? Already picked the captain, right? There's 12 different people who could be captain. That leaves only the remaining 11 people that I could choose to be co-captain. Right? Another minute or 2 here. Another minute or so. All right, guys, let's see what we got here. For number 1, Emma, what did you all multiply together here?
8, 5, 12.
8 times 5 times 12 times 2. What is that, 960? There are 960 different outfits before you wear the same thing twice. I've talked about number 2 a second ago. Let's make sure we got this. How many ways are there to choose a captain? 12. I picked the captain. How many different people could be co-captain? 11. That has tripped people up so far this morning. It's not 12 times 2. It's not 12 times 12. It's 12 times 11. Once you pick the captain, they can't be co-captain. So there's only 11 remaining ways to pick the co-captain. So number 2, 132 different options available. How about number 3? What do you think here, Sylvie? How did you set up number 3? I think I heard that all the way down to 67. Was that right? There's 70 people to be president, 69 remaining people to be vice president, 68 for the secretary, and 67 people for the treasurer. So it looks like there's about 22 million different class officer combinations out there. Does that make sense? Just about 22 million. These can get really big really fast because you're multiplying some larger numbers together. Halfway home, look at these 3. We all good? Okay. Let's see. Option number 4. Panda Express offers 5 sides, 15 entrees, 3 choices for appetizers. What'd you multiply here, Kira? I like it. These are easy. 225 different Panda Express meals available. Number 5 is pretty straightforward. What am I multiplying for number 5? 20 and 15. 20 different styles of shoes with 15 different color combinations gives me 300 Vans tennis shoes to pick from. Number 6, police use photos of various facial features to help eyewitnesses identify suspects. You ever seen like those police sketches? Like in a murder mystery show or on television, right? They're trying to draw the suspect based off of witness accounts. Okay. So let's see, we're gonna have 195 hairlines, 99 eye and eyebrows, 89 noses, 105 mouths, and 74 jaw lines, chins and cheeks. 74, not 64. About 13 billion. Yeah. My calculator put it in scientific notation, but yeah, it's about 13.35 billion. Isn't there? There's not that many people on the planet, ironically enough. Wouldn't a lot of those different options look the same though? You can change one thing and now it's counted differently, right? Does that make sense? I change one little thing and it counts it differently. Put a different eye up there and now it's a different looking person. All right, those 6, what are your thoughts? Easy, right? Okay. Then let me have us add this into our notes. We're going to get into what are called permutations today and tomorrow. So let's discuss what a factorial is first and how we use factorials to define permutations. Does everyone have a calculator out? Not the iPhone calculator, get a different calculator. Desmos, calculator hashtag will be fine. You're going to need not the iPhone calculator for this. Okay. So here's what we got. Factorial. Now, factorial notation looks like a number next to an exclamation point. N factorial is any whole number followed by an exclamation point. It is the product of that first whole number times every whole number less than that, all without a Start with that whole number, multiply it times everything else all the way down to 1. So for example, what would 6 factorial look like if I write it all out? Expand it all out. 6 times 5 times 4, 3, 2. Now let's see where we can do that on our calculator. Here's what we're going to do first. I'm going to waste a little bit of time and type it in the long way. 6 times 5, 4, 3, 2, and 1. 6 factorial, 6 times every whole number less than that, is 720. Now on my calculator, I have a shortcut. I can type in 6, and then on the Desmos calculator, it's under the Functions tab here with this exclamation point option below. What we're going to do in our combinatorics unit here is use a lot of these buttons here in this bottom row. Permutations and PR. Combinations and CR, and this exclamation point. Factorials. So hit the exclamation point, and now it's 6 factorial. It saves you the time of writing it all out. I can just hit 6 factorial and get my number that way. Does anybody need to know where that's at on their calculator? Hasn't found it yet? Your calculator is a little bit different. I'm not sure where. Looks like it's right there. Exclamation point. You see that? So if I hit 6 and shift this, 6. Right. Here's all three. 6. You got the same one everyone else does. See this probability right there? Everything you need to see what's right there. Anybody else need any help? Okay, did you find it? You got the same calculator for those notes here. Got it. Okay. Now let's talk about what a permutation is. A permutation is counting in order. A permutation, by definition, is the way to order, ways to order a set of n objects where I take r of them at a time. I reach into a bucket of n things, I pull out r of them. How many ways can I put that many in order? R of them in order. Ways to order a set of n total objects where I take r out at a time. Notation for permutations is this n permutations of r, n pick r, right here. N permutations of r. From a set of n objects, how many ways are there to order r of them? So the formula is n factorial divided by n minus r factorial. All right, let me kind of show you this in action here. It's track season, so I always like to do this. So here's the situation. In how many ways can 8 runners in a 100-meter dash cross the finish line? Now, before we get too much into this, I'm going to tell you right now. I give you the formula. I never use it. I think the formula is too much work. I think it's a lot easier to just write it out. diagram it out. How many different people can cross the finish line first? 8. That leaves how many people to finish in second place? 7. What do I do with all of these different numbers? Put them all together. You could sit there and type it all in your calculator and waste about 10 seconds. What other option do we now have available? 8 what? 8 factorial. This is just the same as 8 factorial. It's a way for us to save time typing out 8 times everything else before. So 8 factorial is 40,320. You could also use this same permutation formula. How many runners are out there? How many of them am I going to put in order? 8 of them. So from a set of 8 runners, put all 8 of them in order. On my calculator, I can hit this permutation key here. From a set of 8, order all 8 of them. It's the same 40,320. To me, it makes more sense to just do this. Let me give you this. I've changed the situation. Read this question now. In how many different ways can 8 runners finish in first, second, or third? How is this question different from what we just did? Right. I'm ordering how many of them? 3. Right? So let's think about this as a permutation. How many runners are out on the track? I'm going to place how many of them? I'm going to order how many of them? 'They're finishing how many? 3. From a set of 8 runners, how many ways can I order any 3 of them? That's what this question is going to answer, right? Now, I want us to use the formula. I think it's a little bit of a good exercise for us to kind of use the formula. 8 permutations of 3 says, all right, we're going to do 8 factorial on top. Like you saw earlier, this n factorial puts them in order. Like I put the 8 runners in order first, right? 8 runners can finish in first, 7 runners can finish in second, third, 6 runners can finish in third, and so on. Now we're going to divide by n minus r factorial. So n and r, 8 and 3. What's 8 minus 3? So we're going to take 8 factorial and divide by 5 factorial. Would you please expand this all out like we did up on? What does 8 factorial actually look like when I write it all out?
8 times 7.
Okay. 8, 7, 6, 5, 4, 3, 2, 1. I've now put the 8 runners in order. Now I'm going to divide by 5 factorial. What does 5 factorial actually look like?
5 times 5 is 3 times 2.
How could I simplify that?
You just cancel out 5.
5 factorial on bottom cancels out the 5 factorial on top. What am I now left with? Dividing by n minus r factorial stops the count after R have been selected. Aren't I only placing the top 3 runners? How many runners can finish in first place? How many runners can finish in second place? How many runners can finish in third place?
6.
Isn't it just easier to write that out anyway? 8 times 7 times 6 and move on with your life. Okay. So we can do a couple of different things here. Obviously, 8 times 7 times 6 is 336 for your answer. Or you can use the permutations option. Hit that permutation key. From a set of 8 runners, put any 3 of them in order. It's the same 336 either way. It's not too hard to just list it all out. I probably would just do that. Questions you have here? Then let me add on one more. Can I erase this really quick? What's on the list? License plates. In Iowa, license plates on cars look like what? They've got 3 letters followed by 3 numbers. How many license plates are possible? Well, license plates possible. Okay, let's do it. Like I said, diagram it out. 3 letters, 3 numbers. How many letters are there in the alphabet? 26. So there's any one of 26 letters to put first on my license plate. How about next? Okay, it says 25. Did I say we couldn't repeat a letter? Has that been written in the question? So how many letters could I pick from next? 26 still, right? Got to read these questions carefully. They're going to change one little detail and it changes everything about how you're going to put this together. So it's 26 and 26 still, right? I could literally have a license plate that is AAA.
AAA 000.
Sure. Yep. AAA 111. BBB 444. Looks kind of weird, but that's out there. All right, we got the letters. Now let's do the numbers. How many digits are there?
10.
10 or 9?
10, because there's 0.
0 through 9, right? I could do 0 through 9, so that's 10 total digits. What is that number? 26 times 26 times 26. Sounds right. 17. To do before I give you that hint, the one that Taya started to do. Without repeats. Same situation, but without repeats. Why don't you guys try that for a second? How many license plates are there if I have to have all different letters and all different numbers? What's that? There's 10 digits. 0 through 9 is 10 different numbers. I know there's 17.5 million potential license plates if I'm just going in general. Using repeated letters and numbers. But what if I don't want to repeat? What if I want something like ABC123 or XYZ789? What are we thinking here? How many get me started? 26, then,
25,
then,
24.
all right. So as a permutation, this is 26 order any three of them. 26 permutations of 3. Then what's next? Say, Caleb.
10 times 9 times 8.
This is also permutation. I'm putting 3 things in order from a set of 10 digits. 10, pick 3. Multiply them together. What do we get here? 26, 25, 24 times 10, 9, and 8. 11.2 million? What does that mean? What's the other part then? Does that mean there are 5 million license plates that have some repeated letter or number of some kind? I guess it'd just be the other part, wouldn't it? About 5 million license plates that would have to have some sort of repeated digit or letter. Kind of interesting. Okay. Outstanding. So here's the game plan